Welcome to the Project 8P Quarterly Science Update. This particular update, we've got a couple of guests with us, so we're going to allow them to introduce themselves in just a second. This is going to be the first quarterly update that we're going to have a chance to introduce the science team for Project 8P. So we're going to begin by just having them introduce themselves and tell you a little bit about who we have on the team. So Ethan, do you want to get us started here?
Sure thing. Hi, everybody. Ethan Pearlstein, founder and CEO of Perlara, PBC, the first biotech public benefit corporation whose mission is to partner with highly motivated families and foundations to develop treatments and one-day cures for their rare genetic disease. So yeah, my background is as a PhD, and I left my postdoc to start Perlara. The company is actually in its 9th year, and it's kind of refashioned itself during the pandemic, and after a lot of great learnings and a clinical trial success that's now unfolding, it's kind of transformed itself into a pure consultancy. So Perlara is acting as is very, very honored and excited to be acting as Project 8P's globally distributed research team. And so one of the Perlara Cure Guides, as we call them, who are scientists who are super passionate and who have spare capacity and want to devote that to a cause like this, like working with families and foundations like yours. Sam can talk about his background and why he's interested and excited in working as an 8P Cure Guide.
Great. Hi. So I'm Sam Finlayson. Wonderful to meet you all. I am a MD PhD student at Harvard Medical School. I finished my PhD in 2020 in machine learning and artificial intelligence applied to rare diseases. Now finishing medical school and starting a residency in pediatrics and medical genetics starting this spring. Hence a little bit of extra capacity this year as I'm getting ready to start that clinical training. Personally, in addition to my scientific background, which is focused on therapeutic development and diagnosis in the rare disease space, I really came here into this project because I'm extremely passionate about rare disease and rare disease families, and extremely sympathetic to the experience of being a part of a family that's affected by a rare disease. My own sort of life journey is heavily impacted by hydrocephalus, which is a much more common disease than 8P, but I have a sister that was affected by the condition of hydrocephalus from birth and ended up having several hundred brain surgeries and ultimately passing on from that condition. And with my brother, I founded a nonprofit that's focused on developing a cure for hydrocephalus. And I won't spare you with details on hydrocephalus, but something that's very similar to 8P is that it's often thought of as sort of one bucket of conditions, but it's actually a family of related disorders that end up presenting in a similar and very challenging and often sort of easily set aside way by many in the clinical community. And so something that, just as passionate about the science, I'm passionate about this challenge of trying to unite people and help people feel a voice and feel really heard and understood and validated in the challenges that they're facing as they brunt up against the sort of frontier of what the medical research enterprise can offer them. And so trying to do everything we can to maximize what we have within the school skills and tools and knowledge that we have today, but then also sort of using our science knowledge and our ability to organize as communities to try to push against that boundary and break it forward and increase our capacity a bit. So while that's my life experience in hydrocephalus, I'm very passionate about that in a generalizable way, and really excited to work with 8P and any other conditions that I'm lucky enough to work with.
Well, thank you very much, Sam and Ethan, for that brief introduction, and Sam, for your good work in this space. I think that a lot of the viewers are going to have a personal connection to these rare diseases, and I think it's really meaningful that you, who actually have capacity and have the ability and the knowledge and the intellect to be able to really help move this ball forward. It's just a very generous donation of your time and your efforts in this space. So we really appreciate that. So thank you for sharing your talents with our community. Ethan, did you want to kind of give a little bit of background about what motivates you and sort of why you're on board with 8P, and then maybe if time permits, if you can kind of walk us through a little bit about some of the initiatives and some of the irons that are in the fire from the scientific research front.
Yeah, well, definitely what motivates me is originally having, a family member, a sister diagnosed with a rare disease, an autoimmune disease about 10 years ago, actually. And that just made made rare genetic diseases go from a textbook um, example I would teach to second year, biology students to, brought them home, obviously. So I know that's a very common experience that people have when their family touched by rare. And so that activated me, I guess, and then realized I wanted to make my science matter. And what better way to do that than to pair up with people who are so motivated that they kind of end up becoming scientists because they know their child or the disease better than the establishment. And the establishment turns to them to be like, "What do you think? You've seen you've seen more patients than I have with X, Y, or Z." So I kind of realized over time that, oh, I want to bottle that, those superpowers, and I want to build a business around that. Didn't quite figure out how to do that operationally the first go around, but now with this kind of Prolaro 2 and this distributed model, this cure guide model, this more kind of consulting and sort of treating this cure journey as a product, and that we're there to kind of guide you through it, and don't worry so much about the details. We've got that covered, but we want to help you realize that this is a process, and we're helping guide you on this journey. Yeah, that's kind of what's always been the personal sort of what I derive personal meaning from, to be involved in rare diseases as a scientist. So yeah, I think, and I would also add that there is a twinge there of, I told Mina over the years so many times, this is too complicated. This is too complicated. And at a certain point, just said, no, it's not too complicated. And when I finally got to steep myself, and our team got to steep ourselves in AP for the last several months, I definitely come to realize that, oh, the moment is now. And those perceptions about, are these diseases, these chromosome diseases, they're so much more complicated than these single gene diseases. And how do you recreate them in animal models? It's not just one gene, it's many genes. Is there one smoking gun, one silver bullet, or excuse me, one smoking gun that is the gene that's the one that's really the culprit behind it all? Or is there multiple culprits here? Is it a conspiracy? Is a chromosomal disorder is really more like kind of like equivalent to analogous to a traumatic brain injury, or like a spinal cord injury, except to your chromosome instead of to your nerves, because is that kind of an event. And so therefore, it's really, each case is its own, just like each traumatic injury or spinal cord injury is its own case. And so that also led to the perception, this is just too difficult to do anything about. So I'm really excited that Prolaro is now being able to say, we see the science that has changed, and we see the opportunities of therapeutic modalities that didn't exist that can now go from gene scale to chromosome scale. That just never really, the promise of that just never was really as real until this moment. So yeah, we're excited to take that vision of, one day doing what we've done with these single gene diseases and doing that to these chromosomal disorders, these chromosomal diseases. Like, that's not science fiction anymore. And we have, Project AP, I think, has a chance to take the lead. And I think there's several areas that we can move forward on that actually can deliver real tangible gains to the community. And I think, a lot of people know about this concept of drug repurposing and, finding a new use for an old drug, and, wondering, well, what, we've even some medicines got repurposed for COVID. What about, is it possible that there's something out there? And I think we're going to come up with some very concrete strategies for how to do repurposing in many, many different kinds of ways to kind of cover all of our bases. And we can do an artificial intelligence approach where all the papers that are published about AP or any gene involved in that region, this AI can digest all that and come up with repurposing recommendations. And there's a group at University of Alabama, and Professor Matt Might, whose own son was sort of a first patient of a rare disease community, is spearheading this effort. And so, I think that's a very low-hanging fruit that can be pursued. Then there's sort of the next layer of things we can do on the drug repurposing front, where I think what kind of strategic realignment here is realizing that we don't have to wait to figure out all of the pieces of the puzzle here of, well, is this gene really the driver here? And is it for you? Is it for you? What about this? And instead of letting that kind of get in the way of doing repurposing, which I think in some ways, because that's been the playbook for these chromosomal copy number variants, is sort out what's driving the actual problem, and then you can make therapeutic decisions. Well, if we're now in this position where these AP disorders are so complicated, so unique, you're never going to get to that point where or it's going to take a long time to get to that point where everybody's going to have that their jigsaw puzzle sort of figured out. So we can't wait to come up with potential repurposing options, until we sort out all that complicated biology. And so we have a repurposing strategy. In fact, one already underway with a group called RareBase, which is another public benefit company like Prolara, that's focusing on a particular type of neurons in a dish, like so-called excitatory neurons, the neurons that send pulses and are sort of, they're basically doing kind of in the dish what they are hopefully doing in the brain as well. And RareBase is studying the effects of 4,000 different known drugs and their ability to change the level of expression of different genes, including the genes that are in the 8p region. And so it could be a way to figure out if a drug boosts the levels of genes that are in certain deletions, or tamp down the activity of genes or proteins that are in the duplicated region, and so forth. So there's already that stick in the fire, but there's other ways we can do repurposing, and we really, really want to encourage this multi-pronged, diversified approach. So RareBase has kind of covered these so-called excitatory neurons, but what about kind of neurons that are more immature, like earlier, and they're modeling like the earlier brain, or modeling brain development early on? You want to be able to understand those processes. And so we can use a certain type of stem cell, neural stem cell, that comes from the iPS, the so-called induced pluripotent stem cells that have been, that the promise of which is in all the biospecimens that have been banked so far. So I think there are these particular type of neural stem cells that we want to be able to do repurposing screens on as well. And then we even want to keep things really simple and ask, could you even look at skin fibroblasts? And, because those would also have the 8p damaged chromosome as well. Would they manifest some kind of defect where you didn't have to know what was actually causing the defect, but if their mitochondria, let's say, were really stressed out, or some other feature of their cell was really stressed out, like we could look for a drug that fixes that, again, without knowing exactly what was the driver and who was the culprit in your particular 8p rearrangement or copy number variant. So I want to just pause there because I know I dumped a lot of information, but that all falls under this track that we're calling drug repurposing, which is all about saying we want to deliver quality of life gains from medicines that we could get off the shelf, and we don't want to keep waiting for all of that sort of candidate gene approach where we're going one at a time and trying to figure out which are the genetic culprits here in the implicated AP region. Instead, we just want to fix what's wrong with cells that come from AP patients.
Yeah. And maybe something just to add from a sort of a 10,000 foot view, like we don't have a magic wand, nor do we have a single technology that we think will fix this disease or all diseases or anything, and seeing everything through that lens. But what we're trying to do in that light is give us the best shot at really helping this condition in as short a term timetable as possible in terms of making real progress in clinical outcomes. And I think the ultra short term part of that vision is just figuring out the best of what we can do right now. Understanding the natural course of the condition really, really well, understanding pooling expertise across different sites, getting people channeled into the best possible care that we can. And we're thinking about that, although we happen to be calling that track 4, that's like the ultra sort of short, low-hanging fruit. Up a stage from that, there is trying to find existing drugs that have been developed for other conditions, but not for 8p specifically, but that we think would be helpful. And there's a bunch of different ways to identify those. As Ethan was mentioning, one of the ways to do that is to try to perfectly understand this one or more specific genes that are driving the condition. That's how we used to always think about it. But the problem with that is, one, this is such a complicated condition that it's unlikely that we're going to find one gene that's driving all the phenotypes. Two, we have the luxury of now operating in a time in history where we don't have to know one gene to develop one drug to hit that gene to help treat a condition. We can try to directly model the disease state in a dish or in an animal and just try to empirically look at things that will help. Or we can try to develop next gen tools that aren't a drug at all, but are, gene editing and things like that. That, again, those in turn, even just a couple of years ago, you could only think about maybe hitting one gene at a time, but now there's this expanding toolkit that could potentially work at a whole chromosome level. And because that's so on the frontier of knowledge in terms of our capacity as a scientific community, we're not going to put all of our eggs in that gene editing basket because there is a lot to still sort out there. But we do want to use everything at our disposal at sort of every time scale possible, at every level of risk, that we can, to just give us the best possible shot at helping move the needle on this as quickly as possible. So what we've sort of done is try to sort of talk to all the experts we can, read all the papers we can, talk to the people that are affected by the condition, like you guys, and try to organize sort of what are these different types of approaches that we can take, and what are the things that we can do right now to give each of those the best shot at helping us as much as possible in the near term. So that's sort of how I think about our sort of grand view here. And I don't know, have we shared this document with the community yet in terms of sort of what our proposal is? Okay, so we've drafted this document that'll go sort of through all these different types of approaches that we've suggested. And we're sharing this and offering it to the community, and would love to work together to try to sort of make these happen, and also make sure that they're reflecting the goals that you guys have as a community.
Yeah, that's great. I love the immediacy of it. I love the idea that there could be potential accelerants to the scientific process. I think that's going to resonate for a lot of folks that are living with this every day. And so, you can't come too soon. What are the potential advantages or disadvantages to this kind of approach as a strategy? Can you walk us through kind of the new thinking about engaging in this kind of science in this way?
Yeah, so I think the repurposing specifically has reached a point where I think enough people have seen successes, not for every single disease, because the approach hasn't always been taken yet. But I think enough people are seeing that the moment is there for you to try repurposing for your disease, because at a minimum, it's a relatively modest investment relative to what it could give you. And even if you don't get a drug out of it or a drug recommendation out of it, it can kind of, there are learnings from it. So even the failure there would tell you, okay, let's not do that again, or let's not waste any more time doing that. So I think the moment is ripe to just seize repurposing and do it in a way that makes sense for AP. I think there's also this other opportunity, and it's a track in the plan that we've laid out, and that really gets to this point that Sam has been making and that we've been making, is that we can take a lot of these modalities, these therapeutic medicines, these different classes of medicines that we are now applying to these single gene diseases with great success, and taking diseases that would have been slow death sentences or just a lifetime of suffering, and saying there is now an alternative to that. There's actually something that could be quite curative, and we're saying that can be expanded to the chromosome scale. And it's going to play out in so many different ways that it's going to be hard to predict. But I think the unifying message should be we want to develop, or we want to identify drug repurposing opportunities that act in the here and now, but we want to make a down payment on this vision of a future where these therapeutic modalities work at a chromosome scale, and all of the things that work at the single gene scale will have a analog or a version of them that work at the chromosome scale. So for CRISPR or gene editing, instead of being able to make one edit at one location, maybe you're making simultaneous edits, and you're also maybe moving around large stretches of chromosome, not just little bits that contain genes. And for duplications versus deletions, that will create different sort of avenues, right? And so we'll want to be cognizant that there might be certain next generation gene editing technologies that will work great with duplications, and others will work great with deletion scenarios. And so we just want to make sure that you're making this down payment on a cure has this idea that we're going to be seeding. There's not just going to be this one chromosome therapy to rule them all, is what I'm trying to say. There's going to be these different flavors of chromosome therapy. And the real vision is one day imagining if you can have essentially the equivalent of molecular surgeons being able to go in even as early as in utero, once a diagnosis was confirmed of a chromosomal abnormality, and being able to have that molecular surgeon go into the cells of the body and make corrections, and meaning either get rid of sort of the damaged chromosome, and then maybe even set the stage for grafting in a replacement. And I think we can already deliver genes, right? One gene at a time. We know there's a payload limit, but we're soon going to be in a place where I think those limits are going to go away. And so we can introduce entire chromosomes and artificial chromosomes essentially to put back what was missing. And so I think that sounds very science fiction-y, but I can tell you, you talk to cystic fibrosis patients in the 90s about a world where they could take a pill and it could act as a functional cure. I think they would have thought that was insane too. But I think we're in a similar position where you can, it sounds maybe very science fiction, but instead of it being 1990, it's 2022. And I think what took 30 years back then is going to take a lot less time today. And so I think what we want to communicate is Project AP is going to make lots of bets in this sort of chromosome therapy space, because it's a moonshot. We don't know which one is going to win and which will pay off, but we know that we're going to have to be investing in this, because that is the root cause. The root cause is the damaged chromosome. So the repurposing is really a patch, and it's a way to reroute or the compensator to deal with the lesion that's there. And then of course the damage that has been done. You ultimately, to address this at the root cause, the way you think about single gene diseases, you have to make the correction or you have to replace. And so that same mindset, but expanded to the chromosome scale, that's got to be the same threshold for sort of what establishes a cure. But I think you get there in stages, of course. And so repurposing is that first step you have to take, and it's the least expensive relative to all the other sort of things you'll be doing, and it has the potential for the biggest payout, at least early on. And then the dividends will start to pay for the investment in these more moonshot chromosome therapies.
Yeah. So awesome. And the way I sort of think about it in terms of risk is that we have two sort of very synergistic strategies here. Because this is a disease or a family of diseases that is driven by changes in up to several hundred genes, as we know. And we as a society know how to make drugs. We know how to look for them. We know how to test them. We know when we find one that we know sort of how to go about searching for them. And when we find one, we know how to develop them at scale and get them to people often very cheaply and quickly, and it's great. So if we can run that system and try to find drugs, traditional drugs that will help the 8P space, and there's a very good chance that there is some drug sitting on the shelves there that have been developed for some other condition that will be helpful to people for people with 8P changes. And so there's sort of, in a lot of sense, the technology is very robust. The way to develop it and look for those drugs is pretty sort of standardized at this point. We can run that system and there's a good chance that we'll find something that will help in the short term. But what is the likelihood that we will be able to quickly and cheaply find a drug that is going to perfectly offset all of the hundreds of genetic changes that happen in any given 8P hero, particularly when you pay attention to the fact that every 8P hero is a little bit different from the others? It's very unlikely, relatively speaking, that we will find one drug that is going to perfectly cure this condition. So we need to be realistic about that drugs are great. We know how to work with them. We know how to develop them, but it's going to be hard to find one magic drug that is going to cure this condition. On the other hand, gene editing is perfectly suited for this type of problem, because for every given 8P hero, we can know exactly what genetic changes have happened. And if we have the tools off the shelf to just completely fix all of those changes, you would have a perfect cure. And in other conditions, as they've started to be able to do this that are simpler conditions, usually affected by one gene, they have cures, and they have cured conditions that were death sentences in the near past. And so gene editing as a paradigm is a perfect fit. The problem is that we are living at the transition point into the future on this technology. And there are challenges in AP that make it hard, relatively speaking, to develop a gene therapy. And so we need to hedge against the fact that I don't know if it's going to be 10 years or 100 years or 150 years. I would make $1 million bet, all of my money, that in 150 or 200 years, every single AP person is treated with gene therapy. The problem is I have no idea how to bet whether that's happening in 5 or 50 or 100 years. So because it's going to be dependent on the development of ongoing technology that we've made miraculous leaps in the last 10 years, the last 20 years, but we just don't know where we sit in that curve and where are we going to get in the next 5 to 10 years. So we are trying to balance those risks against each other, where we have a very robust technology that is sort of an imperfect fit for the condition that we hope to execute on in the near term, and a perfect fit technology that is just still, in the grand scheme of history, quite immature, which is gene therapy, that we're trying to make this sort of longer term bet on. And how can we strike the balance of pursuing both of those things simultaneously to give us sort of our best average case of helping as many people in this space as quickly as possible?